Zhen. I'm really happy to share my my recent research about my dark journey with sourced Millicharged particles and dark photons. Here I emphasize being sourced. That means I will control my source of Millicharged particles and dark photons, which differs from other type of experimental searches. Okay, so this talk is made up of two parts, but they have a common origin. Right. So where we are now in particle physics, we are really right now in a journey to the unknown and seeking opportunities for new physics. We are standing on the very extremely successful establishment of elementary particle physics and the standard model. And we want to understand what nature has been prepared for us for the underlying theory and deeper principles. Okay, so we are trying to all the different methods, but today in particular, I want to talk about a generic hidden sector with a hidden photon, right? As we all know, we have in our sector we have our own electromagnetism with photon as force mediator and charged particles being the matter content. Here it's reasonable for us to postulate in general gauge extension, thinking there's a hidden hidden sector ENM, and they can have their own forces and electromagnetism, and also hidden electrons, etc. The question is we can postulate this, but the key question is how we can find evidence or test for that hypothesis. It becomes extremely important is how these two sectors connect to each other. Because we are fully in our visible world with our electromagnetism, we want to see if there's a trace of the hidden sector into that can manifest themselves in our sector. Okay, a commonly postulated scenario, which is allowed by quantum mechanics, is a mixing between a hidden photon field and our photon field. We typically call it the kinetic mixing. There are many other mechanisms can generate the mixing, but generically it's determined by some UV physics, and such coupling can be very small. Now, but the Lagrangian is very typical, right? Our standard model sector hidden U1 force mediator plus a kinetic mixing angle epsilon, and also the hidden photon can acquire mass with various mechanisms. It's a simple and heuristic. It's a building gauge symmetry. Can be viewed as spontaneously broken or acquires mass through Zuckerberg mechanism. You can have massive dark photon. We can have Millicharged particles via this effective mixing and talking to the particles over there. Can also have ultra-light dark photons and many other extensions. Although the series are simple, there's many aspects we can explore, and the phenomenology is very rich. And in fact, just to make our story simple, in the first part, I will not talk about the hidden photon at all. I will just for the simplest setup, let's say I have a particle that has a very tiny hypercharge. Okay, and the effective after electric symmetry breaking, there's a fermion field to pick up mini charges under our electromagnetism. Okay, so when we start thinking about Millicharged particles, that's how it looked like back in 2019 when we were thinking about this. Okay, so we're thinking maybe one can the shady region are the existing constraints on Millicharged particles as function of their mass and their fractional charge. Can be 10 to minus 1, can be 10 to minus 3 of the standard model charge, etc. The constraints mainly come from the SLAC medical experiment back in the 1980s, and also collider explorations. But you can see a lot of space are quite open. And there are quite a few proposals of building auxiliary detectors for various experiments to look for such particles. But nowadays, if I grab the Millicharged particle summary plot from one of the recent SNOMAS reviews, we can see as functional mass versus a fractional charge. There are so many, all the dashed lines are the new proposed experiment. People are trying to build a new experiment to look for Millicharged particles. For the reasons I mentioned already earlier, one, it's a good physics opportunity. The physics is simple and heuristic, but also can arise in many different model setups. On the other hand, the rise of Millicharged particle interest can be also associated with various astrophysical and cosmological probes. For instance, Here's a plot I grabbed from our colleagues who are trying to explain the edges anomaly using mini-charged particles, making them a small fraction of dark matter. But still, you can see there's a large parameter space that can help explain the anomaly and yet to be probed by those various proposed experiments. But in this first part, let me first discuss how should we think about mini-charged particles and how do we look for them. Okay, so the first question we want to ask is where can we produce them? As a particle physicist, I really want to have a good control of my source. And we turn our eyes into the neutrino experiments. As we all know, neutrino experiments, in particular, long baseline neutrino experiments requires shooting a highly energetic proton on the target and produce tons of standard model particles. They can subsequently give rise to the neutrino flux. However, here we also foresee such a collision will give a chance to produce the mini-charged particle in pairs from such effective coupling. Okay, so the good news for the neutrino experiments is they have reasonably high beam energy, allows us to have access to GeV scale physics, and also it has really high beam intensity, which means in collider language, we will have high luminosity, which means I really produce a huge amount of them. And even better, we have ongoing and planned future neutrino experiments that can provide as such source for free on top of their original design physics goals of neutrino physics. But let's take a look. The strong beam of the neutrino experiment actually means a strong signal. Again, we can imagine there's various processes to produce the mini-chargeable particle pairs through the collisions, proton target. Here's one example of our calculation. For a mini-charged particle mass in units of GeV, and the vertical axis is how many of such neutrinos can be accepted by a detector that is 1 kilometer down from the interaction point, which is the initial experiments we're looking into. The good news, even for a fractional charge as small as 10 to the minus 2, you still have more than 10 billion of mini-charged particles coming from pion decays, three-body decays. And also you have various pseudoscalar mesons production, as well as vector meson, as well as draw-in process. You have a whole spectrum of productions from this 120 GeV proton hitting a target at rest. Okay, and one should be somewhat impressed by such a number, more than 10 billion of mini-charged particles accepted, because we produce the mini-charged particle at the origin when the beam hits a target. They travel through where we put the experiment is about 1 kilometer downstream. And this experiment we were initially looking into is just 0.5 meter by 0.5 meter by 1 meter, literally a tabletop, right? For most of your tables, you can fit such experiment. Well, it contains 0.5 ton of liquid argon, which I'll mention later. But importantly, such a small size of a detector, a kilometer away from a target, can still accept so many mini-charged particles. This actually tells us the calculation estimation can be done in the following. Each time a proton hits another proton or neutron, it produces on average about 3 pions. The pions have 2.3% times epsilon squared, the branching fraction into mini-charged particle pairs. And the small detector accepts about 10 to the minus 5 fraction of them, even though it's a forward region, but it's so small and so far away, we lose a lot of the flux. But nevertheless, we still have a huge number of mini-charged particles. This highlights the power of having a strong intense beam. Sorry, I think my cat's tail is in front of the camera, but I hope you don't mind. Okay, you can see my screen. So let's take a look at the production and their typical kinematics. As a function of mini-charged particle energy, if they are from pion decay, they are typically like 10 GeV or 5 GeV peaked at those locations in energy. But if it's from a heavier meson decays, they actually have a higher energy. This is really due to the detailed kinematics of the fixed target experiments, as well as the high high mass of those underlying resonances that you need to hit. If it's from draw-in process for very heavy mini-charged particles that they can dominate, they will really have essentially take half of the beam energy. So we can see that we have tons of mini-charged particle produced in a typical neutrino experiment, and they are energetic. Having understood their production, the second question we want to ask is how we can find them. Okay, finding them is a straightforward in diagrammatically, right? They can exchange the photon and scatter with the electrons. For instance, the liquid argon experiment, we can scatter with the electrons in the atom. Okay, the differential cross section will be the following, but in the high energy limit, where the mini-charged particle mass energy is much larger than the mass, electron mass, and as well as the recoil energy, which is how much energy you give to this electron, so that it's a visible particle can see that. Okay, it's really as simple as inversely proportional to the recoil energy squared divided by the target mass, surprised by alpha squared epsilon squared. It is dominated by low recoil energy. So for typical liquid argon experiment with the energy threshold of 1 MeV, for the charge of 10 to minus 2, the mean free path is about 1 kilometer. Okay, so one should have this number in mind. That it means, for typical experiment, the chance for this object to interact with my device is very low. It's 1 in a kilometer. And we don't have a kilometer-sized detector at all, right? The detector I was talking about is about 1 meter. Okay, so this implies that we are going to pay a high price, low chance for my signal detection. Okay, but now let me spend 2 minutes on the liquid argon detectors, which some of you might not be familiar with. Is actually the designated detection technology for current neutrino experiments in the US. Okay, so they are large, clean, and allows for tracking and calorimetry, and also have high resolution, can give us a particle ID. It's basically a bubble chamber quality of data with added calorimetry due to the drifting and collection. Okay, so here's a typical image, and some of you have seen those if you have been working on the neutrino anomalies. There's a whole history of many different types of liquid argon detectors. The one we talk about actually run about this first part of my talk actually run about 13 years ago. Took 5 months of data because it was one of the first generation of demonstrators for such technology. But nowadays there are many new experiments being built using similar technology. In particular, recently last month, the short baseline neutrino detector has been put into the experimental hall. And in the long run, the Dune long baseline neutrino experiment will be built upon this technology. So what we discuss here today will be also applicable to future experiments. So having understood this, let's ask the question, how do I see these mini-charged particles? Okay, let me remind you, it's dominated by low energy transfers, low recoil energy. Okay, but here's a typical image how an event look like at my detector, liquid argon detector. Okay, so you can see there are many visible energy depositions. Drift tells us how energetic they are. There's different vortex, etc. So you can see, you can do various modeling and do particle ID. However, that is not our signal. The signal for today's talk is the mini-charged particle give you very tiny amount of energy, just barely above the threshold, because that maximizes your detection rate. That the energy is so small that the excited electron don't even pass a certain length. It just small hits on the screen. So you can see all those faint dots can be your signal. Okay, and that immediately tell you it's a very challenging signal. There are so many soft hits that everywhere in any detector experiments, can be from slow neutrons, photons, cosmic electronics, radioactivities, etc. So, for instance, for the 10 to the 6 image or event they took for the Argonaut experiment, the tabletop-sized pioneering prototype liquid argon experiment, about 13% of them have already more than one small hits in them, and 1% of them have more than 2 hits. This actually tells you that there's a lot of background to worry about. in particular, unlike our high energy collider experiments, where we have the standard model at high energy to predict the background, we can calculate and subtract, etc. For those such type of experiments, many of their background are environmental and hard to predict. You can do some modeling, but you can never subtract the full amount. So they all have a sizable residual of background. So the question is, what can we do with that? Okay, if we cannot predict a background, our signal is very background-like, and we have a huge number of background. That means implies we'll have terrible sensitivity. But then we begin with our idea. Okay, counterintuitively, we propose to look for two hits. If you recall, the mean free path is about 1 kilometer or longer for epsilon 10 to minus 2. If epsilon 10 to minus 3, it's 100 kilometers, but the detector length is 1 meter. So having two hits means I pay another 10 to minus 3 to 10 to minus 5 signal probability. How come this can help us gain something? The real art is really reside in the understanding the detector feature. The detector actually have really high spatial resolution. Although it's a 0.5 meter by 0.5 meter by meter level detector, its spatial resolution is millimeter level, which means I can imagine if it's coming from a signal of Millicharged particle I produce at the target that goes through a detector, it leaves two hits. These two hits can be connected to a line that point back to my target location. And if it's a random noise background, this random 2 points from radioactivity, etc., they will point to a random direction. The high spatial resolution here can be of use and allows us to do a 5 order magnitude reduction of the background rate. Okay, so for the first time, we brought up this such a search technology, and we make our projections. Back then, we projected that if you do one hit without the ability to subtract the background fully, your sensitivity will be this yellow line, which again already probing new parameter space. But we were not satisfied. We think that has too many limitations. We then proposed to look for two hits, aligned two hits signatures, which gave us this sine curve that tells us we can cover much more space. Okay, so one thing I want to highlight here is that this is a log parameter space, and the signal rate for two hits, which I'll mention later, is a proportional signal background ratio is proportional to epsilon to the 6th power. So any improvement in such a parameter space means huge improvement in signal background ratios. After our projection and theoretical study, we work together with the experimentalists to let them open the data. Okay, so they can open the data, fold in the various experimental uncertainties and detailed considerations, and having a lot of back and forth. Eventually, they agree with my theoretical prediction of the number of backgrounds. They unfold the events, try to connect the two hits and the random two hits they have, and point back to the location of the target where I produce the particles. If the location overlaps with the target size, we say it's coming from the target, maybe our signal. And here's the arrow bars for those events. You can see they have different arrow bars that depends on the resolution and the separation between the two hits in my detector. Okay, so I predict about 1.46 background events from random noise, and they observe one event consistent with our signal signal requirement. Here's how the one event look like. There's two energy depositions. If you connect them back, it points straightly back to my target location. Okay, and this is very consistent with the theory expectation. Okay, so here's a new limit we derive. Working with Argonaut collaboration, after unfolding the data, we find these new limits, which dominates the sensitivities in the 100 MeV to GeV regime, to a field GeV regime that really, as I mentioned earlier, is epsilon to the 6th power sensitivity. So it's really a huge improvement in signal background ratio. This highlights our original intuition. That is, the neutrino experiments with high intensity is a good source for new physics that is light enough that can be accessible for those experiments. But when we ask a natural question, what's next? We know the next big thing in the US is the Dion experiment, long baseline neutrino experiment. 300 times larger intensity, higher luminosity, right? 240 times larger detector for this near detector, and 2 times closer. Basically, this tells me the signal flux will be 5 to 6 order magnitude larger than the Arc-Newt experiment. However, if we do not do the 2 hits strategy, if we just do 1 hit, because we cannot subtract the background, well, we will be coming back to the sensitivity of 1 hit searches. There's no improvement compared to the Arc-Newt 1 hit search. But if we can do 2 hits, aligned 2 hits experiments, following our protocol with timing and others, you will be able to further extend the sensitivity to this regime, 10 to minus 3 in this large regions. Okay, so there's a lot of things to look forward to. In fact, there are many other future improvement that the experiment will bring in via new technology that we are thinking about and working together with our colleagues trying to improve and extend the sensitivity. But having said this, I want to back and reflect about this detection. Okay, the signal scattering, we understood how we find them in the liquid argon environment in the neutrino facilities. But let's come back to the discussion about the detection. Okay, the signal scattering probability and the mean free path, can be derived in the high energy limit. We see it's dominated by low recovery energy scattering. The inclusive scattering rate, that means the rate for my signal to transfer energy to the electron more than a certain threshold is 1 over E recovered energy is surprised. Okay, which actually imply if I lower the energy threshold, my signal rate will increase dramatically. Okay, so here we start to think about a different technology, which is recently has been very successful. That is so-called skipper CCD. For those who are not familiar with the technology, basically CCD is the older version, but ready for your camera. You take images with them, right? There's some noises in the dark room. However, skipper CCD is trying to repeatedly measure the photon, the signal they collect to reduce the noise level. Basically, you can view skipper CCD as a very low noise camera with low threshold. Okay, the skipper CCD most famous one is the Sensei experiment, which gave derived very interesting physics results and won various prizes. Okay, but for us, we started thinking about alternative technology in liquid argon because we are driven by the physics considerations and instead of low threshold dominance. We think if we use the skipper CCD technique, it can increase the signal efficiency by about 5 order magnitude because the energy threshold for liquid argon detection is about 1 MeV, while for CCD is about EV level. In fact, we're looking at 3 electron events, it will be 10 EV, so that's 5 orders magnitude. However, for those who are somewhat familiar with the skipper technology, you will understand the second thing. That is that those are very small objects. Okay, the detection rate is actually proportional to the volume of the detector because it's the angular acceptance is proportional to the area of your detector, and the chance for a mini charged particle to hit something is proportional to the length of your detector. So volume for proportionality volume is a single hit rate proportionality. The Sensei experiment is only 3 grams, which is a tiny, very tiny object, about 675 microns, instead of the 1 meter that we talk about in the liquid argon experiment in thickness. So it's about 10 to minus 5 compared to the Arc-Newt experiment I talked about earlier. So I have a 5 order magnitude enhancement in signal rate, but 5 order magnitude the lower signal acceptance due to the small size. It seems like we're not going to gain much. But the surprise came after we understood and talked to the collaboration. That is, we realized that our recent study with the Sensei collaboration is through repeated, as I mentioned earlier, through repeated measurement of a noisy image, originally noisy image, you can reduce that back to a very clear and sharp image. That's a very slow camera, but a very precise camera. Okay, so it's a very tiny thing. This 3 gram is really just my finger size and very thin, 675 microns, but allow us to make such a precise measurement. Although we don't seem to gain any enhancement due to the rate cancels the small acceptance, but their background is much lower. Recall in the previous experiments in Argonaut, we have 10 to the 5 single hits background. However, for the sensor experiment, when you require more than 3 electrons, which is about 10 eV in the energy threshold of the mini charge particle collision, it has no measured event, so it has no background. So by working with the sensor collaboration, with such a 3 gram of experiments, with 3 days of data taking, we were able to derive a new sensitivity in this parameter region. Mini charge particle versus the fractional charge they have. And you can see the shaded regions has already been quite different from where I showed you earlier in the 2019 paper, because there are many new experiments kicking in, including our Argonaut result. So there's a huge progress. But even in such an intense computation, this 3 gram with 3 days of data has already covered new parameter space, which is very striking. Okay, in particular, if you have been working in this, thinking about such a tiny object versus the half a ton level of experiment, they have similar sensitivity and complementary. It does tell you a lot about the advantage of technology. Okay, but before we derive this result, in fact, this is what was my initial estimation of their capability. Okay, the skipper CCD type of dark matter detection experiment actually have many of those such kind of proposals under construction. For instance, the 3 gram sensei-like experiment, if the 3-day data can derive limits here, but if they took 1 month of data, you can improve to this solid lines. And if you do a 10 kilogram of experiments, such as Oscura, who has already been under construction, if they do 1 month of data taking, they'll be able to derive this yellow dashed lines. And if you do put Oscura in the dune like near detector location, you will be able to derive such dot dashed lines. Again, this is an extremely zoomed out view of the parameter space, mini charge particle versus the fractional charge. Log space, it's a huge improvement, very impressive. Okay, and this time we're exploiting the single hit scattering because of the low background and how thin the detectors are. It's epsilon to the 4th scaling, but nevertheless, it does tell us that new technology does have a lot to say in our exploration of mini charge particles. In the colored lines, I show various other proposed experiments. Again, you can see such experiments are really complementary to the other existing proposals of various kinds. So finally, in the mini charge particle, I just want to also show our recent study with the Oscura collaboration. We convinced them to think about their early physics runs to be in front of the beam, okay, which is what I mentioned in the beginning of my talk. I want to have a stable source of mini charge particles instead of relying on other sources. So you assume you just take 1/10 of the size, 1 kilogram of skipper CCD for the early science. The collaboration has worked out various kind of search strategies, single hit, as I mentioned earlier, or multi-hit. And also they inject certain high-level background just to give a conservative projection. But nevertheless, it shows that a consistent result with what I was showing you earlier in my initial estimation, and tells you that the collaboration are very interested in working together and following our proposal to put in the beam in front of a beam and search for mini charge particles. Okay, so having seen so much limits and projected sensitivities, our natural question we want to ask is, okay, you are good at excluding. You can exclude anything, but are you good at the discovery? Okay, my answer for this question is yes, I think so. No matter you are doing liquid argon or doing the skipper, okay, one can test if the axis events follow expected behavior of the differential cross section that we can calculate. Okay, it allows that to extract various parameters. Of course, this may require certain larger statistics, but once you have established an access, more than 5 sigma level, you have quite a reasonable amount of statistics already. This does allows us to check, for instance, the differential energy distribution for single hits events, and as well as the relation between single hits and 2 hits and 3 hits events. A lot of correlation can be drawn and extract underlying physical information. And also, it's actually a very fast developing frontier. As I mentioned, I want a controlled source of mini-charged particles, but there's other productions. The cosmic ray can hit the atmosphere and produce mini-charged particles. There are interesting recent discussions. And also, we can assume mini-charged particle to be a fraction of dark matter. We have a local abundance of mini-charged particles as a fraction of dark matter, or there's even accumulation effect due to various due to interaction with matter, etc. And that enables new searches, in particular using cutting-edge technology of ion trap heating or cavity-like experiments. On the series side, there's many aspects to improve as well. One can study the signal efficiency calculation using the proper model, nuclear model, as well as the condensed matter model of those semiconductors. And also the production prediction is actually not quite as accurate as our typical energy collider experiment. This involves nuclear physics. So there's a lot of work to do for future for series. Here's another demonstration figure where people think if they are fraction of dark matter, they actually can enable anomalous heating of the ion trap experiment and give you interesting constraints. And this, again, so very zoomed out. You see the mini-charged particle, and you see various other constraints, such as the supernova constraint as well as ineffective. Okay, so this ends my first part of my talk. I don't know if there's any questions. I think it's a good point if people want to ask anything.
Hi, Zhen.
Mm-hmm.
This is Jia.
Hi, Jia. Hi, Jia.
So, I hope to see you in China sometime. So there is a question about the 2-hit scenario. After the first hit, and is there a deflection of the particle in its direction? And then there is some, when you want to connect it to the target, there is some deviation, right?
Great question. Yeah, thanks. Indeed, I oversimplified the story, but each hit you transfer some energy. You actually you lost some momentum, which in principle you will deflect a little bit. So your next line will be hitting somewhere with certain angle. You can estimate what the deflection angle is, right? Recall in the beginning I show you the kinematics of those mini-charged particle produced. They are typically of 10 GeV or even higher energy. The energy transfer here is about 1 MeV. Even if I transfer all of the energy in the transverse direction, I'm only deflecting 1 MeV, 10 to minus 4 in the angle. In fact, we estimated another more important effect that is relatively reasonable, related but closely related. That is, for the particle the mini-charged particle to transpass about 1 kilometer, there are about 500 meters of dirt. You can have random ultra low energy transfers, and those hits actually deflect you as well. The deflection there is less than milli-radian, and we fold that into the uncertainty of the target location acceptance as well. But you're right. If, for instance, if by chance these 2 hits, one of the hits carries a lot of energy, then we have to check what's the deflection. So there will be a bigger uncertainty. We have to assign a bigger uncertainty window in the when they try to connect back to the target location.
Okay, thank you.
Yeah, thanks. Yeah.
Hi, Zhen.
Hi,
Zoe. Hi, this is Zoe. Yeah, hi. Yeah, I have a question on this attenuation. I think you have talked about this attenuation. So, but there's a paper last year by this Milenko group. I think some people working on AA64, they have reanalyzed this slack limit. They found that we got the slack millicule experiments only 100 meters away from the source. They have found that the attenuation of the dirt has some significant effects on these limits. But you estimate the mean path is 1 kilometer in one of your slides. So
that's right.
So yeah, so I try to think what's the difference? Because the slack is only 100 meters. The attenuation effects are already significant.
Okay, so I seem to recall that I've seen that, but I don't recall their conclusion. I thought that they re-derived the slack limit and only changed it by slightly, and I don't recall what they were really trying to. I actually forgot what the effect they were trying to do. So for us, I can concretely say about us. Okay, for us, the mean free path of 1 kilometer is about detection. When you pass through matter, the threshold is not 1 MeV. The 1 MeV for detection. The threshold is tens of EeV level, right? It's basically a question how you can kick an electron, excite an electron in the atom or kick an electron out. There's a typical binding energy, KeV level binding energy. So the threshold there is lower. So you do have a lot of hits. But those hits are like a random walk. You can look at maybe I have I'm not sure if I have in my backup, but maybe when I finish my talk, I can go to the slides. Maybe I have in the backup about the estimation of the deflection, which I mentioned earlier. For us, it's about 10 to minus 2 radian. Which we take into account in our 1 milliradian actually take into account in our signal selection. For slack, I really don't recall slack millicule experiment. I really don't recall their technology. I believe it's some scintillator, and they probably look for some anomalous light. It's quite unclear to me how much they would require the signal to align, to align with the original location. Do they have a directional sensitivity or not? I don't know. I recall I looked at them a long time ago, but it seems like more like a millican experiment nowadays, but just put it in front of the electron beam. And the attenuation for them may well be, if the epsilon is too large, the particle don't reach the detector. So they would put an upper cut on this like millicule experiment instead of affecting the lower cut. The lower part is really low energy, right? It's a low interaction rate. I don't think it would affect this like millicule lower part of their sensitivities. But if you recall more details, you can let me know. I'll be happy to discuss that.
Okay. Maybe I was just a talk. Yeah. So.
Yeah. Okay. Great. Okay, yeah, thanks. Okay, good. Thanks a lot for the nice questions and discussion. I'll be happy to talk more. But I think it's I have 20 minutes left. Let me start the second part of my talk. The second part of my dark journey is called is to look for dark photons in the so-called dark SRF experiment. This is really based upon our recent work now being accepted to publish at PRL that came out earlier this year. So what we're doing, okay? So we're thinking about dark photon, and we understand it's a generic, well-motivated scenario. But the real question is, where do we find them, right? There are many paths ongoing and future searches. Today, I want to share the Pathfinder journey and the results of one such efforts and discuss its future. Okay, so without further ado, let me just show you the result. This is a dark photon mass. What is the kinetic missing angle? And here's our new limits. This is recent work jointly by myself from Minnesota and the Fermilab team. This is so-called SQM-MS, one of the National Quantum Information Science Center. But what we are really using as a particle physicist is trying to utilize their facility to look for new physics. Okay, so the new sensitivity we derive is in this blue shaded region. In comparison to other old and existing experiments, such as Crow's, the old cavity experiment, the Coulomb experiment, as a CMB constraint, we do probe new parameter space again in a log parameter space. It's a very nice new result that we are able to derive and achieve in the past few years. Okay, so but I will not hide the fact. The fact is it's a very active program. Okay, so for typical dark photon mass versus the kinetic mixing angle plot, you see is very, very busy. Here I already do you a favor removing a lot of them. Now here, if we don't assume the dark photon, ultralight dark photon being a dark matter, those are the existing constraints. Okay, if we assume they are dark matter, there will be many more constraints. And what we have achieved in this such a busy plot is we derive a new sensitivity in this space. Okay, of course, our effective coverage can go from here up to very high, very lower mass and larger mixing angles. But as a newcomer, we were shown in the back of other old experiments. So this new result is only our Pathfinder result. There are many more exciting updates to come, but I want to share with you how we arrived here and what to expect in the future. Okay, so the first question is, what is the dark SRF? It's a new experiment. Okay, it's a light shining through a wall experiment. As we all know, we can try to shine light through a wall that is opaque. Okay, we put the detector to detect a photon. We are not supposed to see anything, in particular, see anything at the frequency of the laser. Okay. However, if a dark photon exists in one picture, there are many basis dependence that you can discuss the underlying physics. They have different advantage in discussing different aspects of them. But for the sake of this seminar, let me use a very simplified picture. Just say the photon I produce has a chance to oscillate into a dark photon that can penetrate the wall, which can again oscillate back to a normal photon by play another epsilon chance that can be detected by an active photon detector. Okay, so in alternative, you can understand it as the different propagation modes and the mode coupled to electron and the mode doesn't couple to electron. It tells you more about parametrics and this dependence on the mass of the dark photon. But we can discuss the details if some of you ask later in the talk. Okay, so we know shining light through wall is an effective search method for dark photon. But what is SRF? Okay, SRF is a superconducting radio frequency cavity. We actually, as energy physicists, use them all the time. Of course, as a series, we don't directly use them. But for any colliders or light source we're talking about, the acceleration technology is using our SRF cavities. Okay, we actually have the best cavities in the world as our field as a whole, and they can have ultra high quality and accelerate the beam to a very high energy. You need consistency and lower loss, etc. So high quality superconducting radio frequency is actively being the record is actively being set in our energy physics accelerator experiments. Accelerators. Okay, but as a theorist and particle physicist, how we can use that? Okay, we don't typically talk to accelerator physicists on technology. Right, the reason we think it's an interesting opportunity is because superconducting radio frequency cavities is excellent dark photon light shining through wall experiment. Okay, we basically just propose the following and talk to them. They can grab those ones they already have. Of course, with some extra effort, they can conduct such a search. Okay, basically, you can decide to power up one of the cavities. It will contain a huge number of photons as their high quality factor and high threshold. Those photons would not penetrate the superconducting wall. Okay, in particular, it's the original frequency, which means I should see nothing if I put a detector here. However, if dark photon exists, the high number of photons inside this cavity can also stimulate and induce a dark photon field that is shown in the illustrated in those backgrounds. Okay, so the dark photon field can penetrate the wall. Okay, so here if I put a detector out in a very quiet environment, superconducting a detector, I have a chance to recover, to convert some of the, to see some of the dark photons oscillate back to the probable mode, and I will accumulate some power. And again, being high quality tells me I have a low loss, which means I can accumulate the signal for long and amplify the tiny signal that can, because they're suppressed by the epsilon and many other parameters to be collected here. Okay, so high quality factor and superconductivity actually implies they are automatic light shining through wall experiment so long as you satisfy a few conditions. Okay, so here's the basic naive parametrics. Okay, just to avoid confusing you, I expand all the subscripts and superscript. So the signal power is really proportional. If you understand, if you can work out the phase depends, etc. Proportional epsilon to the force power, square power to induce, square power to receive. The relative phase is proportional to mass over frequency of my original emitter frequency, proportional to the quality factor of emitter and receiver, as well as the power in the emitter. This G factor is the wave function overlap between the propagating mode and my collection mode at my receiver. So I have lots of background noise from proportional temperature, and there's also, you can view the background fluctuation can be controlled by the number of independent measurements. And there's a typical run-up time that is coherent time of my receiver cavity. Just for the cavity we are using, as I showing in the previous slides, its the central frequency is 1.3 gigahertz, and the quality factor is the intrinsic quality factor is about 10 to the 10. It does give you us about 1 second of ring up time. And also there's other background noise levels, but generically it's really as simple as follows. Okay. Of course, in reality, you have to do a slightly harder calculation. Take into the real geometry of those SRF cavity, do the wave function overlap calculation, take into account the high gradients regions and oscillatory part, etc. But nevertheless, the concept is we're doing shining light through wall. We calculate things more properly. Okay, so we have this in mind, and we did our initial estimation and convinced our colleagues, experimental colleagues, who are accelerator physicists, who does not work on new physics searches. So there's a lot of back and forth and convincing them it's a meaningful thing to do. So basically, in the Pathfinder run, back in 2019, after 1 year of our initial proposal, it got assembled and it worked. We are really happy. Okay, so we designed and they make the assembled experiment. This is emitter cavity, this is receiver cavity, and design various scheme to do tuning and doing data acquisition. Okay, and it even allows me as a theorist to go near it, holding a wrench, pretending I can work on it. But to be honest, my wrench didn't touch this object because otherwise I may destroy it. But generically, it's really an emitter and a receiver, and there's a signal analyzer. There's a detailed protocols that we can develop to conduct such a search. But there's our happy experimental colleagues who conduct a search. What the basic idea? Let me see. I have 10 minutes left. Maybe let me give you very briefly. Okay, so basically you can there's a tuner allows you to tune emitter frequency. You can connect the frequency and tuner on resonance with the emitter, and also inject signal to the receiver. You can live monitor receiver power to see if they hit on the resonance. When they hit the resonance, that means the emitter and receiver both at the same central frequency. Then you can disconnect the power line for the receiver and conduct the search, which means here I only power up the emitter. I'm trying to see if anything I can collect in the receiver. If there's a dark photon field, transferring power from emitter cavity to the receiver cavity. And then I can do various steps to connect back to check if they're still frequency aligned. And there's many other intermediate steps I just skip, okay? So, but let's come back to the results, okay? So here's what we see, okay? Basically, we did actually 30 to 50 different steps, for various calibrations, etc. But the basic idea and the basic results is the following, okay? Again, we have to switch language and translate. Here's the frequency of the receiver, okay, power spectrum, and in units of dBm, which is a milliwatt in the dB units. That's our experimental colleague like to use. But the blue lines are the search run, where I turn on the emitter and try to see if there's a power access. The red line is thermal run, which means I don't turn on the emitter with power, don't turn on the power, just sit there and measure the power spectrum in the receiver. So you can see both the emitter and the receiver has a very sharp peak. Both the search run and the thermal run has a very sharp peak at a certain central frequency. Okay, and it's hard to tell if I see any signals or not. So this already zoom in. This is 1.3 gigahertz. I already zoom in by 6 order magnitude. But the quality factor of those cavities are so high that I have to zoom in another 3 order magnitude. So zoom in by 9 orders of magnitude, we finally can resolve the peaks. Okay, so the thermal run is this red peak, and the search run is this blue peak. There's many detailed physics subtleties associated with how the peak deformed a little bit. But let's put that aside. What we did was, let's do a cut and count. Let's choose, there's a noise level you can see on this upper corner, it's very flat, right? So we just take the window where the signal and back, the search and the thermal run both reduce back to the thermal level. Just count the number of photons in the difference between the search run and the thermal run. What we find is they are consistent with 1 sigma level. Okay, there's uncertainties that we can model and calculate with those measured photon counts, and they are really 1 sigma consistent. In other words, we don't find a significant excess in thermal power. In the measure the thermal peak, we actually can identify it's really consistent with the thermal peak compared to the right window. Okay, so then we can derive limits that enable us to derive these new world-leading sensitivities in the dark photon searches using such cavity experiments. Okay, so really thanks to our great experimental colleagues. Again, I only work on the series side and help design many different search protocols. And you may ask, I mentioned that we proposed early in 2018 and conduct experiment in 2019. Why it took us 4 years to get this result? In fact, it was COVID, but that's not a major reason. There are many effects our experimental colleagues was not thinking about because they are not looking for new physics that we seriously think could be correctly modeled and understood. So they have done many additional runs to calibrate and to measure the properties of this to enable us to establish these solid constraints now that we derived today. Okay, and if you have been following the math I showed you earlier, and you plug in the numbers that I show you, assuming you are okay with all those weird units, this is not the result you're going to get. Okay, in fact, if you plug in the numbers and just use the formulas I gave you earlier, all the lengthy formulas, it will slightly more longer than that. The result should be as strong as this. Okay, and the natural question you ask is, what happens between your initial estimation and when you propose the experiment, and what's the pathfinder result? Okay, so I will attribute the last 5 minutes of my talk about this to explain this. And that took us a few years to do our initial modeling, and we're still working on to improve. We do think we can improve the result by quite a bit to reach our original estimation in this first run. Okay, so the story behind is really the high quality factor is not always blessing. I have been emphasizing we have high quality factor, enhance this, enhance that, but that's not the case. Not at least not in the reality. Okay, that was only in the ideal case. It's a double-sided sword. Okay, our Pathfinder result did not fully benefit the Q-square as we initially wanted. We are in a totally different regime that has not been done before in such kind of light through wall experiment. Here, the natural line width, which is omega over Q, is much smaller than the frequency uncertainty, which I will discuss soon. Okay, so after 2019 run, we actually conduct many more searches and validations to allow us to model this properly, to conservatively and initial properly. Okay, the challenge is as simple as the following, right? If you want to if you use a tuner, right, you ring up this one, you want to transfer power to this one. Okay, they have to be at the same frequency. That's how tuner works, right? However, we have extremely high quality, which means the emitter and receiver cavity has to be exactly spot on in their central frequency. Okay, and just to give you a concept, okay, about how aligned they have to be. The cavity size is about 20 centimeter. Quality factor is 10 to the 10. The line width is about 0.13 hertz. For Hertz level stability, one needs to ensure the cavity size does not change at the sub-nanometer level. Okay, I have built a huge object. It has to be stable at sub-nanometer level. So that tells you the challenge. There are many sources can change the size of the cavity by nanometer level. For instance, you put in a liquid, I forgot, hydrogen nitrogen environment, give you 2 Kelvin, low temperature. There's emitting, give you bubbles. The bubble burst on the top of the surface and give you temporary pressure change. That pressure change can change your size by nanometer. Okay, and there are many other effects. They are total together called microphonics and also frequency drift. Let me show you what's the size of those effects. Okay, here's our frequency stability monitoring run. Okay, let's just take a look at how stable the frequency of the objects are. Even though we align them at the beginning, how much they change with time. Our search is only 30 minutes. Okay, the result is 30 minutes of running, but the calibration is much longer. Okay, so you can see the central frequency has changed by about 5.7 hertz from highest point to lowest point over a 100 minutes time window. Okay, on top of the central frequency drift, there's about hertz level up and downs. That is, we call it the jittering, that they vibrate around central frequency. Actually, it's not as small as with 1 hertz level. You won't have to do a dedicated microphonic test run to show you and to study the jittering the frequency up and down size is about 3.1 hertz. Okay, the reason we see 1 hertz in such a monitoring is because of the low sample rate of the receiver frequency. Okay, and this should give you a warning sign already, right? The frequency is drifting at the few hertz level, and the frequency is up and down at few hertz level. Although the line is as narrow as 0.13 hertz, so you will receive penalties that when those two resonances are not aligned. Okay, so there's a lot of estimations and light shapes and how things change with time, but let me just skip that. Okay, so basically, with various measurement, we present a very conservative limit. We basically conservatively model the reduction of the signal rate as the misalignment, constant misalignment of frequency. Okay, which means here's my emitter power. I assume my receiver is trying to pick up a power totally off the resonance. I assume there's a huge gap between their the frequencies between emitter and receiver. This is of course super conservative. It's a 5.7 hertz plus 3 hertz mismatch in drift, and 3.1 plus 3.1 hertz mismatch by microphonics and jittering. And it's clear those are definitely not, this one for microphonics is very conservative. For the drift, one can try to overcome this by monitoring of frequency and also other techniques. Every few minutes, you can realign the frequency, etc. But that's our initial data taking. We didn't anticipate those effects to be much larger than what we have when we initially thinking. Okay, so such a penalty factor tells me my signal efficiency is reduced by 5 orders of magnitude. That generates a big gap between our initial estimation and our derived new limit. Okay, so I'm running out of time, but let me really quickly spend 2 minutes. We understood that, we know how to improve, and there's various theory work and experimental work trying to overcome those difficulties. But we do think in the near or far future, we are able to fully realize the Pathfinder expected results, and we can reduce the noise level further to be in the single, few photon limits for my receiver noise level. And we can further improve Q and eventually have a phase sensitive readout. Each step will enable us to, dive another half order magnitude or order magnitude. Give us a very interesting future perspective. They will allow us to conquer many, many new parameter spaces in this very motivated dark photon stories. Okay? And it's a very active field. In fact, there are many interesting active dark photon, dark matter search, also by our collaboration as well as by Professor Jing Shu et al. In PKU. And one can do axion light shining through experiments as well. There's many papers trying to propose those. But however, when to make sure those proposals are reasonable, as you all see, the reality is all about whether your idea can work out with the noise level you're anticipating. Typically, theorists underestimate the background. Okay, and there's axion dark matter search, gravity wave search and validation, mini particle search, and also one can derive photon mass constraints. There are many new studies and partial summaries in our recent STOMAS activity paper. Okay, so let me summarize here. Today I share my fan journey to the unknown and the physics at different scales. Apart from our beloved energy collider physics, sometimes it's interesting to look at the other aspects. For mini-charged particles, we propose new search strategy and obtain new results and have a lot of good future with liquid argon experiments. And we also have a new search strategy proposed for the skipper CCD techniques and obtain new results, and the collaboration are fully aware and will carry out our proposed study. For dark photons, we designed a new superconducting radio frequency cavity-based experiment, cover new parameter space in a log parameter space. We learned learning how to handle ultra high quality opportunities and challenges. We are establishing and developing scheme for robust test. The field is under development. It has a very active program ahead, many planned steps to improve future sensitivity, many possible theory research direction to improve the result and treatment, as well as discussing what are the motivated theory parameter space. And there's many adjacent explorations, such as axions and gravity waves searches are possible. That's all. Thank you.
Yeah, thank you, Zhen, for this nice talk. Now it's time for questions and discussions. Yeah, you can unmute yourself to ask any question.
Okay. Hello, Zhen. So what determines the frequency resolution of dark SFR? Is the measuring time or other things? Frequency resolution.
Frequency resolution actually is very high, as you can typically use the off-the-shelf spectrum analyzer. They have very high resolution. It's not a limiting factor. You can read off the power spectrum by longer time to even have more fine resolution. However, here, as I show you, the smallest window we're talking about is the intrinsic quality factor, that is 0.1 hertz. Of course, any commercial device would have 0.1 hertz resolution for the frequency. But as I mentioned, maybe more related to your question, I think I want to answer you directly that the spectrum analyzer is not a limiting factor for my frequency resolution, but the frequency stability and drifting are more of the experimental hardware problem that one have to get around. And one thing I forgot to mention is this stability effect. This is really just a performance of the off-the-shelf cavity that people do tests and runs for accelerators. So nowadays they can design new ones and trying to do spectral treatment. The property will improve quite a bit. I wouldn't say there's a hard floor and limitation of instability of frequency of hertz level. I think one might be able to overcome that.
Okay, thank you.
Yeah, I hope that answers your question. Thanks, Jen.
Yeah. Hi, Jane. I have a question. Yeah, this is
Sean.
Shredam. Yeah, I met you several weeks ago in Pittsburgh, at Pittsburgh.
Oh, great.
Yeah.
Great.
So I have a question. So can you give us some intuition why your excluded region, the shape of excluded region looks like that? Because we know for cavity experiment, for cavity experiment, the excluded regions, just like the needle is very thin, is very narrow. Why?
Very good. Very good question. Okay, so let me give you a typical experimental lines. Okay, so here left one is a dark matter search. If you see the screen, right? So if you look at it, it's a super narrow line. So actually, if you look at this one, dark photon mass versus the kinetic mixing, it's typically a narrow line because all are narrow resonance searches, right? So those are the dark matter searches. What they are doing is I put a cavity there, who are trying to pick up a signal at a very narrow window, right? If my dark matter happen to be at that frequency, I will excite and I will see that. So those are narrow band search. However, that is not what we are doing. What we are doing is, you are talking about why is this shape, right? So the shape is driven by the fact that, as I mentioned in the title, we are doing a sourced experiment. Okay, so the emitter cavity is trying to emit a photon field at a high frequency, like 1.3 gigahertz. Okay, so it actually allows me to excite any dark photon with a mass below that frequency. I have a powerful source, right? I have this mass. Any dark photon mass below that, which means you will just pick up some kinetic energy. So having a powerful source allows me to have a broadband sensitivity. However, the sensitivity shuts off very quickly, right? Because if the dark photon mass is heavier, I would not actively excite that mode. But for lighter dark photon mass, we'll be exciting that. It will be this way. And there's a very interesting detailed question about why the slope is like this. Okay, so that is about what's the probability and what's the parametrics of light shining through wall. The light shining through wall is actually proportional to the relative frequency development between the photon field and dark photon field when they try to propagate. So the relative phase is, of course, they have same energy, right? But they have different momentum. So the relative phase is proportional to the mass. Under small mass over frequency limit. That's why the parametrics is as the following. There's also another interesting question about whether you're trying to excite the longitudinal mode or transverse mode, etc. But nevertheless, you can see in a dark photon mass going to zero limit, there will be no relative phase. So I will never oscillate into a dark photon mode, and I will not do such experiment. That's why the sensitivity decreases. It's a broadband search, but decreases to zero when it becomes really massless. Yeah.
Okay. Thank you.
Yeah. Thanks.
Is there any other questions? Yeah, I have a naive question about the detector for the Millicharged. So you mentioned this liquid argon and the skipper CCD. So is the germanium detector possible for this kind of searches? Or is there any particular requirement on the detector properties?
So the parametrics is actually as this summarized in this single slide. So whatever technology you are trying to come up with, you need to ask the following question. Okay, I think the flux is very easy to understand. I just need to put into intense beam, right? And it will need to be reasonably shielded, so my detector won't be polluted by all the other induced background. The question now is about what's my value of my detector and what's my threshold to have reasonable background under control. Okay, so germanium detector, if I'm thinking about the typical dark matter detector, the direct detection experiments, their threshold is higher. Okay, is instead of the sensei which their selling point is a low energy threshold. Their threshold, I don't know the number, maybe KeV or something like that.
Yeah, one
tells
KeV.
Me, yeah, the KeV threshold, which means the signal detection rate for a single hit is about 100 times weaker, right? which means you can compensate that by 100 times larger volume if you are able to build a big one. And then you need to look into, with such a threshold, KEV threshold, do I have a lot of background? If I have a lot of background, do I need to employ the double hit strategy, which reduce my signal rate by another few orders magnitude, or I need to increase the threshold to reduce the background? You can do this back in the envelope and estimation to see if they are promising or not. My generic intuition is intuition is unless the germanium technology can be produced in a large volume detector, and also have a low background as low as skipper, etc. Otherwise, it might not have a very competitive story. The intuition behind this is because Sensei and others are really proposed to do low mass dark matter detection, right? Low mass dark matter detection because they don't have too much kinetic energy and the energy transfer is low. But the Sensei is winning in the low mass regime. Although germanium is also winning, but they don't win as much as Sensei from a dark matter detection perspective. To a certain extent, our signal is not too much from dark matter, but the only difference is where the beam is a source. We know how much intensity there are, but really we also favor low threshold. Low threshold means a higher signal rate. So the mass is slightly different, but given Sensei is the leading one in this low threshold detection, I expect it probably would be good. But I'm open to discuss new technology, and even though if someone has great device working, I'll be happy. We can evaluate and estimate the sensitivities together.
Okay, good. Thank you.
Yeah.
Hi, Zhen.
Hi,
may I ask? May I ask another question on the attenuation? So when you estimate this deflection angle from the source to the detector, you estimate the angle at what energy, recoil energy?
So let me just open my slides. Give me a moment. Let me see if I can open the slides. Let me see if I have. I think we estimate the typical binding energy of the electrons, but let me just see. I don't know if you see my screen. Let me share a different one. That's actually in my backup. That's good. Okay. So do you see this slide?
Yeah. Yes,
okay.
Yes, we can see.
Okay.
So for Millicharged particle 5 GeV, okay, the typical deflection is 2 times 10 to minus 3, with epsilon 10 to minus 2 and 500 meters of dirt. Okay. So there's an average deflection per collision and time the number of square root of collisions.
Okay. So this angle is obtained by integrate all these recoil energies cross section. So or just estimate at this threshold your detection.
Right. So it's a very interesting story. In detail, let me try to describe a bit. So in terms of energy loss, is actually dominant for relativistic particle is dominated by single hard scattering. But in terms of number of collisions, is actually dominated by small energy transfers. By low energy recoils because they have a higher rate, but it's like a random walk. So there's square root of number of small collisions. So the estimation for energy loss and for angle deflection is actually two different regimes. And we really follow the particle transpassing through matter discussion in PDG in carry out such a calculation. I don't know if that helps you or not, help you explain or not, but I think you are asking something more profound. Yeah, can you elaborate a bit more? Yeah.
Yeah, I was actually thinking about the cross section when you go to lower energy range and below the threshold of detection, but the cross section goes up, and I think you also already mentioned So there's a lot of collisions when the particle passing through the matter. That will not give you a lot of energy loss, but maybe they will have some effects on this angular deflection. I didn't do the calculation. I'm just wondering whether in your calculation you have taken this into account of this angular deflection.
Right.
For those low energy.
So if you see the orange curve I draw on the screen, do you see the orange curve?
Yeah, I can see it.
So that's a typical dx plot for relativistic particle. This region is relativistic, right? So this region, huge energy loss is dominated by the Cherenkov loss, but this region is really dominated by the beta block equations, and energy loss. Again, as I mentioned, this plot in this regime of relativistic particles dominated by single Hart scatter. That's not the calculation we did here. The calculation we did here is trying to trying to take up there's a separate calculation that is actually logarithmic dependence on the threshold that you can work out and calculate the deflection. I think that's what you meant, but we did use that calculation that is logarithmic and follow the PDG formulas there to derive this effective deflection angle. So low threshold, multiple scattering. That's where the root n come from, actually. Yeah.
Okay, so your calculation goes below the threshold of the detection.
Yeah, definitely. As I mentioned, the 1 MeV threshold is our detection. It's not the threshold for this calculation. The threshold for this calculation, I think, is the typical binding energy of the material, which is the KV and below. So it's a much lower one, but much larger number of collisions. Okay, and again, there's a very interesting discussion, in the particle transpassing through matter section of the PDG. I learned a lot from them. But as I was mentioning, this piece is actually captured by the log piece in the DEDS calculation, which actually is multiple scattering and low threshold. Yeah.
Okay. Thank you.
Yeah. Thanks. Okay.
Is there any other questions? Yeah, if no more, let's thank our speaker again for this nice talk, and we will end this seminar here. Yeah. Thank you. Thank you, Zhen, for this nice talk.
Yeah, thanks everyone. Great to see many of you here, and I really hope to discuss further. If there's any question didn't answer clearly, feel free to reach me, and I will be happy to discuss more details. Thanks.
Good. Yeah. And could you please send the slides to us so we can also post it on our website together with the video?
Sure. I can send that. Okay.
Yeah. Thank you.
Yeah. Okay. Thanks, Yingcheng, and good to see everyone here. Okay.
Yeah. Thank you. Have a nice
night.
Guys
soon. Yeah. Hope to see you guys soon in other occasions. Bye. Yeah.
See you.
Bye.